right, we have a velocity versus time graph. It says that there's the whatever different sections. I want to know which segment does the car have the greatest distance. So distance would be the area, because that's how you get distance or displacement from a velocity versus time graph. So we've got these three sections, and if I were to kind of look at the areas, seems pretty clear that AB is the greatest area, so it'll be the greatest distance. Which of the following is true? It's at rest from B to C. No, because being at rest would be a velocity of 0, that would be down here, so not true. The average acceleration from A to B is less than the average acceleration from C to D. So let's think about acceleration is the slope, so average, right? It's not a constant slope, but that's okay. This one goes up 8 over 1, 2, 3, so A to B would be 8 over 3. From C to D is 8 over 2. I'm pretty sure I meant that to be the magnitude. But either way, right, this one is less. Oh yeah, yeah, I meant that to be magnitude. 8/3 is less than 8 over 2, which is just 4. Slowing down from D to E is getting faster, right? That's negative velocity and negative acceleration, getting faster, so not true. Position at C is the same as position at E. Let's look. So that would be true if these areas canceled out. So this is 8 times 2 over 2, so that's 8. And this is 1, 2, 3, 2 over 2. So that's -6. Positive 8 and -6 do not cancel out, so that is not true. So yes, B, I definitely meant that to say magnitude. All right, another velocity versus time graph. We've got 4 kilogram object, 3 segments. For A, there's an applied force. For B, there's a friction force. And for C, there's a second applied force. First, I'm just looking at displacement, so let's do our areas. So looks like A, but let's just double check. 2 times 2 over 2 is 2. This one is 2 times 1, which is also 2. And then 3 is definitely less. So A and B are actually equal. And then C. And all of them are positive areas because none of them have like a negative height below the x-axis. So A and B are equal, greater than C, all of them greater than 0. So C. Here, how does the friction force compare with the applied force? So I drew a little free body diagram because we had a lot of forces going on. So let's say this was FA1. In B, we still had the FA1, but we also had friction force. And then in C, we still had the FA1, and then we took away the friction but put on like an FA2. For this one, obviously accelerating, see how B is at a constant velocity? If it's at a constant velocity, these forces are going to be balanced, so FF and FA1 are going to be equal. How does FF compare to the FA1? Equal. How does the applied force in C compare to the applied force? So how does this compare to this? Now you'll notice in C that it is slowing down. So because it is slowing down, that means the negative force or the against force will be greater. So the FA2 is definitely bigger, so we can cross off A and B. Now I just need to figure out how many times greater it is, right? Is it twice as great or not twice as great, basically? So let's look at our original acceleration. This one had an acceleration of 1. This one had no acceleration, which is how we knew it was balanced. This one has an acceleration of -2. So because I know that I'm slowing down, right, I have negative acceleration, this force is definitely greater. Now it is an acceleration of -2, so I'm slowing down with a greater acceleration than I was speeding up here. So that means my net force here is greater than my net force was here, obviously negative, right? So that means I not only had enough force to cancel this one out, I had like a bunch extra to be slowing down super fast, so this must be even more than twice as much force. If it was exactly twice as much, right, that would be enough to balance out, plus this would be a net force the same in the other direction, that would have a slope of 1. All right, here, what is the change in kinetic energy in A? So change in kinetic energy is 1/2 mv² minus 1/2 mv², final minus initial. The mass is 4. Initial velocity was 0, final velocity was 2. This goes away, half of 4 is 2, 2 times 4 is 8 joules. In B, I didn't change at all, right? It's 2 and 2, so constant velocity has 0 change in kinetic energy. Don't need the equation to tell me that. If there was no friction, so if there was no friction, A would have continued like it was going. This had a slope of 1, so I'm at 2 right here. If I go over 1 more, I would end at 3. So my initial velocity would be the 2, but my final velocity, if I took away that friction, would have kept going and would have been at 3. So then I do my change in kinetic. 1/2 4, 2 squared. This is 18 minus 8, which is 10 joules. So here, change in kinetic, 1/2 mv squared minus 1/2 mv squared. I know my mass. I just need to look at my graph to get the two velocities. Now, for the first two, it was easy, right? Initial velocity of 0, final velocity of 2, then it was 2 and still 2, gives me a change of 0. The last one, though, said what would it be if there was no friction, so that one I had to just continue the line, right? Continue it at that same slope and find, okay, initial is 2, it would have been 3 if it had kept going. Part is moving with a constant acceleration of +2, so A is +2. At t equals 0, so that's just at the beginning, the velocity is -8. What is the motion after 1 second? Oh, at t equals 1 second. I'm going to sketch a graph. So this is -8 and positive slope. If I start at -8, after just 1 second, I would have gone up 2, so I would have gone only to -6. So see how that's in this section of the graph? This is a negative velocity with a positive slope. That's moving in the negative direction, because we're looking at the velocity, and it's opposite, so that would be slowing down, see? Now if I looked at t greater than 4, so 4 is exactly where it crosses the x-axis, because a slope of 2, right, it would go over 4 to get up to 8. So then now, this is the second part I'm looking at. Here I have a positive velocity with a positive acceleration, so moving in the positive direction, and same sign, that means they're speeding up f. While A is dropped from rest, at the same instant B is shot horizontally. Who takes a longer time to reach the ground? So thinking about the time it takes to reach the ground, I think about their accelerations. They each have the exact same acceleration, the acceleration due to gravity. So they're going to take the exact same amount of time to fall down. So they will have the same time because they are falling the same y distance with the exact same acceleration. Now, who has the greater speed before hitting the ground? So this one I'm going to use conservation of energy. So A has potential energy, B has both potential and kinetic. So when they get to the bottom, right, then this guy has more energy in the system. So when it's all kinetic, he'll have more kinetic than this guy. So who has a greater speed? B. The other way to think about it is they have the same acceleration down, so they'll have the same velocity down, but B will also have an x velocity, which means he's moving faster overall than just this one. A ball is thrown up into the air at an angle. When it is at its highest point, what do we know? So I'm going to make a note, the y velocity is equal to 0. Now, if the y velocity is equal to 0, that does not mean the x velocity is equal to 0. In fact, x velocity is constant. It's still going to be moving to the side. It is an equilibrium. Equilibrium means that like it has a no acceleration net force of 0. At the top, it definitely still has the force of gravity that is not being balanced out, so not equilibrium. 0 acceleration, no, has the acceleration due to gravity. Gravity didn't turn off. It's at its maximum kinetic energy. So maximum kinetic energy would be where it's fastest. This is actually the opposite, right? It's at its maximum potential, which means it's at its least kinetic energy, so not true. It has no forces acting on it, not true, we've got gravity. It has no velocity, it has no y velocity, but does have an x velocity, so none of those were true. Constant speed, force p, which of the following must be true, so I'm going to sketch my normal weight, this P gets broken up into P sine and P cosine. And then friction. It says constant speed, so that means balanced. So that means N plus P sine is equal to your weight, and F is equal to P cosine. So let's think about if I were to rearrange and get N by itself, N is weight minus P sine. So N is not equal to the weight, it's equal to the weight minus something which is less than the weight. So N is less than the weight. So N is less than the weight. Oh man, that was literally the only one that says N less than the weight. But I knew that P was going to be greater than F because I know F is equal to P cosine. P cosine is only part of P, right? So if only part of P is equal to F, then the whole P will be more than that because part is less than the whole. The whole will be bigger than the part. Here we've got frictionless surface. If the angle were to decrease, so at first you've got F sine and F cosine. If you were to decrease the angle, you have less F sine and more F cosine. So same thing here. So I'm just going to kind of look at this. So if F cosine was going to decrease, well, I still need these three to balance out. So if this one decreases, then the normal must increase to make up for that. So normal force will increase. And your acceleration will definitely increase because now you have a greater net force in the direction of your motion. You have a greater F cosine. So increase and increase here. Here, find the frictional force. It looks like I'm definitely using FF equals mu Fn because look at your answer choices. That's the way we're going here. Draw your free body diagram. You've got mg. This tension, or if whatever, it's not really tension, but it's going down and to the right. So that would be T sine and T cosine. And then normal force up, friction force this way. I want to get Fn, so Fn is equal to mg plus T sine. I'm going to take this and substitute in for Fn, so Ff is just mu times that whole thing. So mu times mg plus T sine is A. This one there's a typo, it says 1 on 2, this one should be 2 on 1. But actually doesn't really matter because the force of 1 on 2 and the force of 2 on 1 are the exact same force. So F12 and F21 are going to be equal no matter what. And weight 1 is the weight of box 1. So we are drawing, or we're ranking the forces. So either way, F12 and F21 are going to be equal. So I'm just going to put that in, right? No matter what was happening. Okay, now I'm looking for how does the weight compare. So weight of box 1, if I draw my free body diagram for 1, we've got the weight of box 1 pulling down, and then we've got the force of 2 on 1 pushing up, F2 on 1. Now whether these two are equal or one is greater just depends on the acceleration. So now I'm going to read moving up and slowing down. Moving up means the velocity is up, slowing down means acceleration is opposite. Moving down means velocity down, slowing down, acceleration is opposite, so up. Moving up, velocity up, speeding up, acceleration in the same direction. Moving down, velocity down, speeding up, acceleration in the same direction. If you're accelerating down, then the weight 1 is the bigger force. So weight 1 is greater than these two in both cases where the acceleration is down. If you were accelerating up, then F21 is bigger. So in the two cases we're accelerating up, the force between the boxes is more than the weight. Right, block of mass M is on a ramp at an angle of theta. Give an expression for the force to move at a constant velocity up, and there is friction. So I've got my normal force coming out of the surface. I've got gravity pointing straight down, but that's going to break up into the mg cosine, mg sine. Cosine is across from the normal. I'm using that because I am talking about breaking down the weight on an inclined plane. Don't use it in any other circumstance. It says moving up the ramp, so the force needed, so that's some force F, that's what I'm looking for. And then the friction would be opposite to the motion, so if I'm moving up, the friction would be down the ramp. And it says constant speed, so that means the forces are going to be balanced. So then F is equal to these two, so F is equal to the force of friction plus mg sine. I was not given force of friction, so I better substitute in. This is mu Fn plus mg sine. And looks like my Fn is equal to mg cosine. So then last step, substitute in for that. And there's my force needed to go to constant speed. Here, mass is pulled, rough inclined plane, force exerted. Find the acceleration in terms of F. So the friction force is given. I don't need to replace it with mu Fn. So very similar free body diagram to the last one, mg cosine, mg sine. You've got normal force. It says that it's accelerating up, so friction force, F, is going this way. The only difference is that force is not long, so I need to break this one up. That is pushing both up out of the ramp and along the ramp. So this would be the adjacent side, so F cosine, and F sine is up out of the ramp like that. They are not balanced because it says it's accelerating. So then F net is just F cosine. And then I need to subtract both of these, so minus mg sine and minus the force of friction. Find the acceleration, that's just ma. So then all I need to do to get a by itself is divide m over. And there's your acceleration. Find the coefficient of friction. Leave it in terms of these. So I know the force of friction. So if FF equals mu Fn, then that's just little f equals mu. The normal force here, so let's make a note, Fn plus F sine equals mg cosine. So then subtract over mg cosine minus F sine is my normal force. So all I have to do is plug in for there. To get coefficient by itself, I would just I would divide over Fn, and then now I'm substituting. Mu is F over the normal force, which is mg cosine minus F sine. We've got cylinder set in rotation. The floor drops away, leaving suspended one person of mass m. There's coefficient, radius r. How fast is it rotating? So I'm going to draw my free body diagram because this guy is definitely hanging there, has force of gravity. It says the floor drops away. It's still going to be hanging there. So I definitely have a force up. It is not the normal force because the floor is not pushing him up anymore. So let's think about it. He wants to slide down. The force that is holding him in place, if there's no physical surface, must be the friction between him and the wall. Remember, friction goes along the surface and it opposes motion. And then the reason he doesn't fly out is because the wall is pushing him, so that would be the normal force of the wall pushing out like that. We're going to write a net force equation, but it's something moving in a circle, so we're going to call it centripetal force equation. The centripetal force is provided by the normal force here, and then I know these two are balanced because he doesn't slide up or down, so FF equals mg, so that's mu Fn equals mg. And then centripetal force is mv squared over r. Now, I am trying to find v. I don't know what Fn is, so I'm going to take this and substitute in for Fn. Now it's in terms of all things that I know. Trying to get v by itself, cross off an m, multiply r up, divide mu over, and then take the square root. The velocity is square root of gr over mu. Twice the mass, 3 times the radius. What is the gravitational field? So gravitational field is gm over r squared. So if I have twice the mass, 3 times the radius, that would be times 2 ninths. And then compared to Earth, so Earth's is 10, so then this becomes basically 2. It's like 2.22, something like that. If gravitational field is twice that, and I have half the mass, what happens to the radius? So half m, what are we doing to r in order to get times 2? So, okay, so I have half on top. In order to get times 2, you need times 4. Which means you must be dividing by 1/4, because dividing by 1/4 is the same as multiplying by 4, which is what you would need. So dividing by 1/4 means you need a 1/2 here for when it gets squared. So 1/2 the radius would be radius divided by 2 feet.